Everything humanity has ever seen, touched, or observed adds up to a rounding error in the grand ledger of the cosmos. All mapped stars, planets, and galaxies represent only a tiny fraction of what is actually out there. This chart shows the composition of our universe as we currently understand it. Ordinary atoms account for just 4% of the total. The rest is divided among unseen components, including a massive 23% share belonging to cold dark matter. In modern cosmology, this is defined by the lambda CDM model. The CDM stands for cold dark matter. Cold means these particles are sluggish. They move far slower than the speed of light. Dark refers to the fact that they are transparent. They do not emit, reflect, or absorb any form of radiation. Because these particles are heavy and slow, they clump together to form an invisible web across the cosmos. This acts as gravitational scaffolding that pulls in ordinary gas, collecting it into dense, glowing pockets. This initiates a bottom-up formation process. Small clumps of dark matter merge, creating deep gravitational wells that eventually ignite stars and build entire galaxy clusters. Without this invisible glue, the galaxies we observe would lack the mass to hold themselves together. They would simply fly apart, meaning the structures required for our own existence depend entirely on this unseen scaffolding. But if this substance is invisible to every sensor we possess, how can we be sure it actually exists? We know it's there because of gravitational lensing, a phenomenon where gravity itself reveals the unseen mass. Dark matter halos may be invisible, but they still possess immense mass. And in general relativity, mass curves the geometry of space itself. When light from a distant galaxy passes through these curved regions, its path is forced to bend. From our perspective, the background galaxies appear stretched into curved arcs, revealing the optical distortion left by something we cannot see. These observations provide proof that the mass exists, but to understand what dark matter actually is, we have to move from the scale of galaxies down to the scale of subatomic particles. The search for a specific particle relies on finding a candidate that fits the cold and dark profile, something heavy enough to exert gravity, but light enough to stay invisible. One prominent candidate is the WIMP, the weakly interacting massive particle. These are theorized to be heavy enough to drive galaxy formation, but they only interact via gravity and the weak nuclear force, allowing them to pass through ordinary matter like ghosts. Another option is the axion. Unlike the heavy WIMP, axions are ultralight. They were originally theorized decades ago to solve a different problem in quantum physics, but they happen to behave exactly like the dark matter we observe in space. Then there are primordial black holes. Stephen Hawking theorized that microscopic black holes could have formed in the extreme density of the early universe. Scattered across space, they would interact only through gravity, accounting for the universe's missing mass without requiring new particles. Because each of these candidates has different predicted weights and behaviors, researchers can build experiments designed to test for them individually. To find these particles, we have to go underground. By placing laboratories nearly a mile beneath the Earth's surface, researchers use the planet's crust to shield their experiments from the constant noise of cosmic radiation. This is where you'll find the LUX-ZEPLIN, or LZ experiment. It uses 10 tons of ultra-pure liquid xenon to create a highly isolated environment for detecting rare particle interactions. It waits for a dark matter particle to bump a xenon nucleus, releasing a telltale flash. Yet, the LZ experiment analyzed its massive dataset and detected nothing. Crucially, by recording 0 collisions, scientists eliminate specific mass ranges, narrowing where these particles can hide. We are systematically ruling out the most likely possibilities. If dark matter is a particle, this process of elimination is slowly forcing it into a corner. While we search for a single particle underground, a second hunt is expanding into deep space to map dark matter on a cosmic scale. Previous flagship observatories like Hubble have spent decades studying the deep universe, but their view was always limited to very narrow patches of the sky. The next generation, including the Nancy Grace Roman Space Telescope and the Euclid mission, will have a much wider field of view. Their goal is to survey billions of galaxies at once. These missions will use weak lensing, measuring the tiny shape distortions in billions of distant galaxies to conduct a massive statistical analysis of the invisible mass between them and us. This data will allow astronomers to construct a three-dimensional map of the dark matter cosmic web as it appeared 13 billion years ago. By constraining the particle's mass in deep underground labs, while simultaneously tracing its structural history from orbit, we are finally aligning the physics of the very small with the structure of the very large.